All right, let's jump right in. AI is totally shaking things up in healthcare. And one of the wildest areas is medical imaging. We're going to talk about how these machines are actually learning to see, to understand scans and images, and how that could completely change the way doctors do their jobs.
The timing for this couldn't be more perfect. Our healthcare systems are just stretched to the limit. We've got rising costs, more and more people needing care. It's a ton of pressure. And that strain, well, it creates this perfect opening for a technology like AI to come in and give our amazing doctors and nurses a helping hand.
And that really is the million-dollar question, isn't it? It's one thing to talk about making things more efficient, but can a piece of code, an algorithm, really make the same kind of complex life or death calls that a trained doctor makes? That's exactly what we're going to get into. So to really get where we're going, you got to look at where we've been. And this whole AI journey, it's not new. It started way, way back in 1951. But the real game changer was in the 90s when machine learning came along and let computers actually learn from data. Then came deep learning in the 2000s, giving it a structure kind of like a brain. And now things are moving so fast that by 2025, we're seeing huge regulations like the EU AI Act just trying to keep up.
Okay, so how does this all actually work? I mean, to really understand how AI can look at an X-ray, we have to first get our heads around the basics of how a computer even learns to see anything at all. This is the foundation for everything that comes next. The absolute workhorse of computer vision today is something called a convolutional neural network, or CNN for short. And the coolest part? The whole idea was inspired by how our own brains see the world, the visual cortex. Yeah, that's right. We basically taught a computer to see by copying the way our brains pick out edges and shapes and patterns. Let's break that down real quick. A CNN has three main jobs. First, you have these convolutional layers that act like little magnifying glasses, scanning the image for basic stuff. A straight line here, a weird texture there. Next, pooling layers come in and shrink everything down, basically saying, okay, let's ignore the noise and just keep the most important clues. And finally, the fully connected layers look at all those clues and make the final call, like a detective saying, yep, this is a picture of a cat, or this scan has a problem.
Right, but seeing isn't just one thing. Depending on the problem you're trying to solve, you need different types of vision. It really all boils down to one question. Do you just need a simple label for the entire picture, or do you need to find a bunch of specific things inside of it? And this shows the difference perfectly. On one hand, you've got image classification. It looks at the whole picture and slaps a single label on it. It answers the question, is there pneumonia in this X-ray? Simple yes or no. But then you have object detection. It goes a huge step further. It doesn't just tell you if pneumonia is there, it tells you where it is by drawing a little box right around the problem area. Now, image classification is super useful. Don't get me wrong. It's great for quickly sorting things. But it has its blind spots. If the thing it's looking for is partially hidden, that's called occlusion, it can get totally confused. It also gets tripped up by what we call background noise. Think about trying to spot a dangerous mole on skin that has a lot of freckles. It can struggle to tell them apart. Object detection, on the other hand, is usually way more accurate because it's looking for specific things in specific places. But it's also a lot more sensitive. Change the camera angle, change the lighting in the room, or if a tumor is a slightly different shape than usual, it can get thrown off. So it's this constant trade-off, right? Simplicity versus this really detailed but sometimes fragile precision. Okay, that's enough of the theory. Let's make this real. How does all this come together to solve an actual problem you might find in a hospital? This is where you see how you pick the right tool for the job. So let's put you in the driver's seat for a second. Imagine you're building an AI to help doctors sort through thousands of chest x-rays. What do you choose? Do you go with a simple yes-no label of classification, or do you need the specific boxes from detection? And here is a real-world problem a person posted on Reddit. They're trying to build a system to automatically spot litter and potholes from a camera on a moving car. So what's the answer? It has to be object detection. And here's why. Just knowing there's trash somewhere is useless, right? You need to know where it is so you can log its GPS location. You need its location to make sure you don't count the same piece of trash 20 times as you drive past it. And you need to know where it is to ignore stuff that's not even on the road. The location is everything. So, just when you think you've got a handle on how these CNNs work, guess what? The whole field is already taking another massive leap forward. There's a totally new way of doing this, and it thinks about pictures in a completely different way.
Say hello to large vision models, or LVMs. These things are monsters. They're built using something called a transformer, which was actually first made for understanding language. And that's the wild idea here. It treats an image less like a picture and more like a sentence made up of little visual words.
So how in the world does it read a picture? Well, first, it chops the image up into a bunch of little squares, called patches. Then it takes each little patch and squishes it into a line of code. That's our visual word. Then, and this is key, it adds a note about where each word came from in the original picture. Finally, the transformer looks at the entire sequence of words all at once, which lets it understand how every single part of the image relates to every other part. So let's put them head to head. LFMs, these new transformers, they usually give you higher accuracy. They're better at learning new things. But all that power is expensive. They need a ton of computing power to run, and they're harder to understand. They're more of a black box. CNNs are the reliable old pros. They're faster, they're cheaper, and they're perfect for very specific, well-defined jobs where you just need one thing done really, really well. Look, this technology is incredibly promising, but making it work in the real world of healthcare, well, that's not just about writing better code. It's about people. It's a human challenge. And there are some really tough hurdles we have to clear. For starters, if you train an AI on data from only one group of people, it might fail completely for everyone else. That's algorithmic bias. And then there's trust. If a doctor can't understand why an AI made a recommendation, how can they rely on it? And we haven't even talked about the big legal questions, like who's responsible when it makes a mistake, or how we protect all that sensitive patient data. These are the problems we have to solve. And all of this brings us to what might be the single most important point of this whole conversation. The goal here is not to replace doctors. It's to build amazing tools that help them, that augment their skills. Let the AI do the tedious, repetitive work so doctors can focus on what only humans can do: complex thinking, talking to patients, and providing care. And to make sure we build these tools the right way, clinicians can't just be sitting on the sidelines giving feedback. They need to be in the driver's seat, leading the development. Their expertise is the only way we can build systems that are truly safe, effective, and worthy of our trust. So, when you boil it all down, the future isn't some far-off thing. It's here. This change is happening right now. The real question for all of us, for patients, for developers, for doctors, is not if AI is going to change medicine. It's how are we going to guide it to make sure it changes it for the better?